Okay, good morning. Okay, let's continue on the causality of the system. Okay, does the math work? Okay. So we started this topic in the last lecture already. We have talked about signal causality, and then we talked a little bit about system causality. Okay, but we haven't really formally write down the definition of that. So that's what we're going to look at it, and we'll also look at a couple examples. Okay, so look at how to determine the causality of a system. Signal causal or not causal, okay, that's pretty straightforward. You basically look at, is there anything for t less than 0? If there's nothing there, then it's causal signal. Okay? But for system causality, you have to check it. Okay? So here we look at an example in the previous lecture already, and I wanted to write down the formal definitions first. Okay. So here's the formal definition here. Okay, a causal system is one type of system. Okay, for this kind of system, the output at any instant, okay, at any time t naught, the output depends only on the values of the input. So let's say if the input is f of t for t less than or equal to t naught. So this is a diagram we used in the previous lecture. If the input is f of t and output is y of t, okay, here is a system. So that's more of a formal definition for causality of the system. It seems to be very straightforward to understand. Basically means if you look at the output at here, and the output, okay, it doesn't matter what time. If I'm looking at arbitrary time t naught, there will be certain maybe expressions, okay, associated with this output y of t. If the system is causal, then this y of t naught, the output, depends only on the values of the input f of t for t less than or equal to t naught. So it can be maybe, for example, it can the y of t at here could be just equal to f of t, or y of t here equal to f of t, for example, plus f of t minus 2. Okay, so then for this case, I get y of t equal to, for the first one here, I basically get y of t equal to f of t naught. And for this one here, we get y of t naught equal to f of t naught plus f of t naught minus 2. Right? So those are two examples. If this is the actual output, then the output at any time t naught will be given by this expression and that expression. So if you look at the first expression, what it tells you is the current output depends on what? The current input. Right, so this is a t naught representing the current input at t naught. And the second one tells you the current output, so let's call this as current output, okay, equal to this one here is the current input, and this one here, f of t naught minus 2. What do you think I should precisely call it? If this is the current, this one here more precisely, what we should call it what? Future? Why should it be a future? Because this is t naught minus 2. The past, right? So this should be the past input. I'm referring to this whole piece, okay? Not just the t naught minus 2. So this should be the past input. So this second case, the current output depends on the current input and the past input, which is perfect normal. Yes?
Would that mean it's non-causal?
It's causal, actually. So you look at the definition. If it's causal, whenever the output depends only on the values, the input for t minus t, t less or equal to t naught. So essentially, if your output value depends only on the past or the current, then you have a causal system. Okay, so the idea here is system is causal if output, okay, depends only on the past and or current inputs. Okay. No future inputs got involved here. That means it's a causal. Whenever your system actually depends on future inputs, the output of the system depends on future input, then it becomes a non-causal system. Okay, something called acausal. So, for example, here, let's see another example we did in the previous lecture. So let's see if y of t equal to f of t plus f of t plus 2. Okay. So if you substitute any time moment, so at t equal to any t naught, suppose the t naught is the current time moment, it is very obvious that your current output depends on the current input plus this guy here is what we call future inputs now, right? That's the future, because the t naught plus 2, that's the time compared to the current time t naught. That's the future time. So that's why it is a non-causal system. Okay. So this is non-causal. These two are causal. Okay. So causal or non-causal is a very straightforward, I think it's a logical system. In reality, you know, if you learn a little bit of philosophy, it's always basically about cause and effect, right? So you put in some cause here, then there will be an effect. Okay. But you know, a real-time system, right? The cause always occurs before the effect, and that's called causal. Mathematically, you can definitely have a cause or effect happen before the cause. Okay, you can definitely have that. So effect you can consider as an output, and cause you can consider as input, right? Yeah. So that's if you relate to actual system, right? That's something like that. So in reality, just remember, real systems all causal system, right? But we do sometimes see non-causal system mathematically. So let's take a look at a few examples. Let's see how we can properly determine the causality of a system. Okay. Any questions so far regarding the definitions of causality? Okay. Let's look at a few systems. Let's look at the first system, which is y of t equal to 1 plus x of t, okay, cosine t plus 1. So in this case, in the following three examples, our x of t is input, and y of t is output. Okay. So this is the first system, y of t, the output equal to 1 plus x of t times cosine t plus 1. What kind of system is this? Is it a non-causal system or is it a causal system? So I heard somebody say non-causal. So how do you make a conclusion so quick? Yes? So you saw the t plus 1 here, right? Yeah. Now that is a very natural mistake you can make actually for this kind of first question here. So you're so focused on the current and the future, but then you forgot input. But you look at this one here. Is this the input? That's not the input. What is the input here? X of t. This is the input. Right. So when you determine the causality of a system, you're looking for the keywords is the output, right, depending on the future inputs or not. So it's the input-output relationship. Other than these two, don't worry about it. Those are probably comes from somewhere else, right? For example, like this one here, I could draw a system like this. If this is x of t as the input, okay, then there could be a multiplication factor at here, and then maybe a 1 constant adding up to the next signal, and then here's your output y of t. So basically your system, the black box, inside the black box, right, contain those components at here. So the system, first of all, take the input, multiply by cosine t plus 1, and then this plus another one here, and give you the output. Right. So what's in the system could be this. Your relationship, this is still your output. This is still your input at here. Okay. Yeah. So now, if this is clear, you look at this system here. What do you think? Is it a causal system or non-causal system now? It has to be a causal system, right? So if you substitute, basically, now another challenge for this kind of part of the system characteristic is not like a regular mathematical proof. You know, you plug in an expression, you started to write down derivations. At the end of the day, you say, okay, you know, this A equal to B, you proved, right? This part, it's more or less you had to prove it by framing your procedures onto the definition. If it applies to the definition, you know, it's a causal. If not, then it's not causal, right? So most often for this kind of question, you could always do is just pick an arbitrary t naught. Okay, pick a t naught as your current time, and plug it into the. You could pick an actual number. Okay, you could pick an actual number here, not just a variable t naught. So if I pick arbitrary t naught, plug it in, I can always get y of t naught equal to 1 plus x of t naught and multiply. Okay. So then you look at your relationship between your output and input, and it's clearly that your current output depends only on the current input, which is fine. That's that falls into the causal system category, basically. So that's why this is causal. Okay. Yeah. As long as you can show this, then you can make a conclusion that it's causal. Okay. So let's take a look at another one here. Now this one is a little bit different. Okay, it could be confusing. This is your output y of t, and the y of t, right? This again, here is your input x of t, and here is your output y of t. Okay, inside is the system here. So what the system does is essentially it's integrating. And integrating from 0 to positive infinite. And what is the integrating? It's integrating this x of t minus tau d tau. Okay? Yeah. So what do you think about this system? Do you think it's a causal system or a non-causal system? Bearing in mind of the relationship, it's always a relationship between the input and output, right? And look at the dependency between the input, between the output and the input. Is the system depending on future inputs or not? Or is the system depends only on the current, or the system depends purely on the past? That's the conclusion, right? That's the condition you make use of to draw a conclusion. Yeah. So if you look at this one here, if I do the procedures I did, let's say I'll let t equal to t naught, arbitrary time. Then we ask ourselves, okay, so at this current t naught time, what is the system output? According to the given condition, okay, it's this. So you have a x of a t naught minus tau at here. So maybe for the temporary, just pretend you don't see the integration signs. If you don't see the integration signs, what do you have? You have x of t naught minus what? Tau, right? So if you don't have this one here, what do you think? Is y of t naught equal to x of t naught minus tau? Do you think it's a causal or non-causal? It's causal, right? Okay. So now let's put back this integration sign. According to the first year, what is the tau? What's the proper name for the tau yet? For the tau variable? When you have an integration, the tau right here is called what? Upper limit? No, it's called dummy variable, right? Dummy variable. So what's the range of dummy variable in this integration? 0 to positive infinite. So basically means the tau value is always a what? A positive number. So in other words, you have a t naught minus a always positive number. So what do you think? Is it causal or non-causal? It's causal. But before we move on again, think about the integration again, okay? What's the nature of integration? Sum, right? Excellent. Integration is summing. You're summing so many points together, you get the integration. So in other words, you plug in a tau at a different value between 0 to negative to positive infinite, and then you sum together. That's your integration, right? But in this case, it doesn't matter how you sum, because the tau is always between 0 to positive infinite. It's a positive number. So whenever you plug it into here, you always get a t naught minus a positive number. So that means the current output depends purely on the past input. So that's why it's a that's why it's a causal system. Okay? Yeah. Is that good? So you basically try to bring this abstract equation here, right, a little bit into life, and then you can actually explain it, right? Yeah. So this is a causal because tau is between 0 and the positive infinite. Okay, so it's a positive, and then your y of t, okay, depends on past inputs. Okay. Now, I want you to I don't need you to show this in the actual exercise, but for integration, now if you recall that whenever you have integration, okay, from let's say a to b, the integration basically it's about summations. So you're summing, okay, from I1 to n, and then okay, delta t as a small limit. Okay, and then if you let the n go to infinite, okay, you get essentially your summation or the integration in here. In this case, your n times delta t, okay, will be b minus a. Okay, and then ti here belong to anywhere between a and b. Should use this this bracket here. So you can see you have your integration essentially is a summation of many of these inputs at here, right? But in this case, all of the inputs actually the past inputs. Any questions so far? Okay, so I'll change these questions slightly. Okay, see if you can be tricked or not. Another simple example, very simple. So let's say I have a 0. If y of t is 0 to t, x of tau d tau. If this is the integration, if this is the system here, so output equal to 0 to t x of tau d tau. See the difference is what? The previous one is definitely positive infinite here, right? But here I'm using a variable t, okay, instead of positive infinite. And here is x of tau. Okay, it's like different. The other one's x of t minus tau. So for this system, what do you think is a causal or non-causal? Maybe use what listed here as to help you understand. Right? Anybody care to? You said non-causal. Why is it non-causal? Mm-hmm. Yeah. Where is the future here? Which one is the future input? Let's see.
Summation of the
summation, right? Okay. So, but summation means you're summing all the way from 0 to t, right? So if I replace the t with t naught, so basically means you're summing all the values from 0 to t naught. So you're not summing anything beyond t naught though. Right? Yeah.
If t naught is negative, you will sum your value in between that's greater than t.
Excellent. Excellent. Yeah. What's your name? Sorry.
George.
George, right? Yeah. As George is saying, if t naught is less than 0, there's a little bit different story here, right? So you got to be careful what the t's value here in this question. So let's examine what we're talking about here, okay? So if t is actually naturally defined as a value greater than 0 and or equal to 0, okay? So if I naturally define the t as something greater than 0, maybe 3, maybe 4, okay, or maybe 5. In that case, when you plug in any t naught between this 0 to t, and you can clearly see that your output depends only on the past and the current, possibly x of t naught, right? So this has to be a causal. It doesn't involve anything from the future. But if t is less than 0, let's say for example, let's say t is negative 3. Okay, if t is negative 3, then what happens? Right? So if t negative 3, I put negative 3 at here. Okay. So when you, let's say when you have when you pick sorry, what is it again? So if you pick a value, let's say y equal to, let's say you pick a value t equal to t naught equal to negative 2, let's say. If you pick t naught equal to negative 2, so the current value y of negative 2 involving what? Values of input from negative 3 to negative 2, and then negative 2 to 0, right? That's integration, piecewise integration. Negative 3 to negative 2, that's fine. Between negative 3 and negative 2, those are the past compared to negative 2, right? But then between negative 2 and 0, compared to negative 2, they are actually what? Future, right? So in this case, if your t is a negative value, this system actually becomes a non-causal system. So this is the tricky part. Sometimes you have to be very careful in terms of all the detailed conditioning in here. Most of the time your t is greater than 0, right, when we do integration, right? But if the question actually specifically specified certain t, right, less than 0, then you have to be very careful. Okay. Yes? Oh, negative sign, yes. Negative here. Yes. Does that make sense? Yeah? So the bottom line is, always look for the relationship between the inputs and the outputs. You can set yourself with a certain time moment, t naught, and examine the relationship, see if there's any dependency of the current output on the future inputs. If not, then that's perfect. That's a causal system. If yes, then it's a non-causal system. Okay? Yeah. There will be more exercise in this part here. This is actually, I start to see sometimes you start to get falling into traps or start to getting feel the abstractness of this kind of question. Okay. Yeah. So maybe let's look at an example here. Here's the new system. So y of t equal to x of negative t. X of t is the input. Y of t is the output. And in this case, your y of t is a slightly changed form of the inputs, x of negative t. So if you have x of t, then x of negative t technically is what? Is basically a mirror of this x of t are about which axis? Y-axis. What in this? Yeah, y-axis, right? Yes. Okay, that's actually the first tutorial will give you this kind of brief reviews, okay, on different systems, okay, on different manipulations of signals. So let's come back to this. Is it a causal or non-causal? Okay. Yeah. Depends on sign of t. Okay. So let's say if t is greater than 0, it is a causal or non-causal? It's causal. Excellent. So you have probably done in your head, if t is greater than 0, you plug in any values, right, for the inputs. Doesn't matter what value you plug it in. And it's clearly that the output depends only on the past, right, values. That's why it's causal. So output depends only on the past. Okay. However, okay, if you have a t value that's less than 0, so let's say pick a number, t equal to negative 2. Okay, t equal to negative 2. So let's look at if t equal to negative 2, what happened to the input and output? So when t equal to negative 2, your output is what? Y of negative 2. Right? That's we're talking about the value at t equal to negative 2. So according to our definition, y equal to negative 2, what should be the output according to the according to the given system? X of 2. Okay. Yeah. So you look at this final connection here. The current output depends on the future inputs now. Okay. So that's why at this stage this is a non-causal. So then what do we do then, right? So in this kind of question, if the question specifically define that the t is greater than 0, then your conclusion is causal. If the question, like what I wrote it down at here, I didn't say anything about the t, then your conclusion should actually be non-causal. Okay. But bottom line is, as you can see at here, right? We should check all the time. Not just t greater than. If you're given a question, unless the question specifically restrained their t to be, for example, greater than 0. If the question didn't restrict anything to the t, then you should check all of the times. All the time meaning from negative to 0 to positive, right? All the possible time moments before you draw a conclusion. Yes?
So if he's not defining at a certain meaning, it's just we say that it can be causal or non-causal.
Depends on the t, yes. But in this case here, the t is not defined. that means basically t can be from negative infinite to positive infinite, right? Then your conclusion of obviously will be non-causal. Yeah. Good. Any questions so far on this causality? I want you to exercise yourself. Okay. If you have a system y equal to x of at, and a does not equal to 1, what would be the causality of this system? Okay. There will be some additional exercise when I finish a certain amount of chapters, and post it on Canvas. And there will be basically more exercise relates to causality, and the next like linearity, time variant, invariant. Okay, so you'll have more opportunity to exercise. All right, so let's move on from the system causality to the next system classification, which is system linearity. Okay. So I think I mentioned 3 different classifications. So this will be the second one, the system linearity. Before we give the formal definition of a system linearity, I need to introduce a new concept called operator. Okay, so operators. The reason we're introducing operator is previously, up to now, whenever we talk about system, we have just drawn or sketched a box, right, like this. So we call this is a system. Okay, that's fine, but often in time it does, make it a little bit cumbersome to write things. So we can introduce a mathematical symbol, which is defined as the operator to represent a system. Okay, so essentially we think of a system as an operator. Let's use a symbol m. You can use any symbol you want, okay, to represent this system. So the operator m representing certain system. Now if you look back at what system does, right? So you have a system, and you have input and you have output. So essentially what system does is it will manipulate, okay? It will manipulate the input function, and then manipulate and probably do some kind of action, right, on this input function, which you'll see. Maybe it's a derivative action, maybe it's an integration action. And then it will produce output, which is another function. Right, so that's what the system does, or what this operator does. It acts on the inputs, do some kind of action, which is a function, and produce another function, which is the output. So that's what the system does, right? So for example, we have a very simple system. If I have x of t here, we can have a derivative action, and that produce outputs. Okay, that's a simple system. The action here is a derivative action, right? That's the derivative action acting on the input function f of t, and then produce an output function, which is df of t over dt. So in this case, this is your operator m, right? So this m here is specifically a derivative action operator. So this one here, this d over dt, is a operator. You learn that, your derivative action is an operator. Or similarly, you can have integration if your input is x of t, and producing your output, right, using an integration action. Okay, if you have anti-derivative function, then it's the upper limits minus the lower limits, okay, as the output. So that's the idea of operator. Okay, so the operator essentially whatever inputs given to the system. Okay, I'm using this big M symbol to represent, this is the operator symbol to represent the action of the system. It can be as simple as a derivative, it can be more complicated as, you know, a combination of different kind of things. Now operator is a very common thing. As a matter of fact, sometimes we don't say it in this class. Okay, in this class we'll learn convolution. Convolution using this star as a so-called operator. So what it does is, as you see in the maybe next week, it does an action on two functions, f of t, g of t. Okay, that's called the convolution action. Okay, and we're also going to learn another operator called Laplace transform. And we use this weird L symbol representing Laplace transform. So Laplace transform, instead of an M symbol, right, here is an L symbol. So you're doing transformation on certain function. So that's another operator. Another operator we're going to learn also in this class called the Fourier operator, a Fourier transform. And then it's this F symbol. So that's what we're also going to learn in this class. And in the 248, okay, there's another different kind of symbol called gradient. Okay. Basically, it's an inverted triangle. Yes. This one? This one? Convolution. Yeah. Very convoluted. Convolution. Yeah. And in same class, you have another operator called divergence. So it's a del dot. So don't worry about this. You will learn this in the future, near future. And then there is an operator called curl. So there are numerous actually operators, okay, in mathematically and representing certain system. Those are just representatively operators that we'll learn, you know, in both of these two second-year courses, right? Yeah. So bottom line is we can use arbitrary operator to represent the system, and that's what we're going to do. Okay, from now on, if I have a system, I'll use the M to represent the system, and the bracket, the dot means you can plug in. It's like a bucket. You can plug in anything into that, which probably will spit out a different format of expression for the output. Okay, yeah, that's what operators. So I think I'm going to stop it here. So we're going to use the operator concept to formally define linear and nonlinearity. Any questions so far? needed to me?
I had a question for you.
Yeah, what's your name?
Oh, I'm Caden.
Kim.
Nice to meet you.
Did you take my class, the other class last year?
I didn't.
Okay.
I guess I'm the fifth year program, so I probably didn't.
Oh, okay, okay. Yeah.
I had a question about example 3 about the tau. Or, yeah, the symbol tau.
Yeah. Which one?
Yeah, this one.
Yeah.
I'm not really understanding like what's going on.
So,
like when you plug in values of t,
yeah.
why is
Are we talking about this one or this one?
yeah, this
This one here.
or both?
Oh, both.
Might as well.
Okay.
Yeah.
So,
Oh no, sorry, not this one. Yeah, this one.
this one? Yeah. A better understanding, as I always see, is to break it into this kind of place. If you recall that, maybe you know what? Just let me stop this first.